Okay, I'm gonna go live. Woo, we're good. I'm going live. YouTube.
Countdown.
I guess there's no countdown. It's just gonna go live. Why are you trying to connect to the Wi-Fi?
They can definitely hear you because there are emojis.
Okay, good. Ladies and gentlemen, we are going live on the internet. But am I still connected? Because now it's trying to make me go on Wi-Fi. No, I'm still good. I'm gonna turn my Wi-Fi off.
Yeah.
Yes.
So that it doesn't try and do some. And hopefully that won't kill the live stream. Okay. So you're good. Can anybody say if they can see this live streaming on YouTube?
YouTube is live. Yeah.
I'm gonna.
We're seeing.
I'll get rid of the
So
participants.
we can see the participant list.
Okay, good. So I got rid of that. All right. I think we can get started. Can we get started? Yes?
While we, just for funsies, while we do the introduction, Rocio, maybe can you not share your screen and let everybody, we can go into gallery mode so everybody can see who's here?
Sounds good.
Because there's a really nice community online.
Okay.
So if you could ask people to maybe turn their camera on and say hi to everybody. So
Hi,
we can
Sarah.
see.
Hello.
Yay!
Hey, everyone.
Yay. I guess I'll,
Yeah, I guess I can turn my video on too.
I'll do a screenshot. Yeah. Oh wait, I'll put my camera on too.
We can also show who's in the room.
I don't know. I think it has, does it have to go, well, it could go through anybody that's here. Okay, I'm gonna take a picture. Everybody smile so we can then get started.
Okay, I'm gonna leave it. So that there's like a picture
Okay, yeah.
in the room.
All right, I think we should get started because we're 10 minutes. So the microphone is gonna be Rocio's. I'm gonna pin Rocio, but she will be pinned. I think this is gonna work. And then we'll do intros. So we'll do a twofold intro. I'll say a couple things, Kelly will say a couple things, and then we'll get started. I guess I can unmask.
Do you want to come here?
Behind the podium.
Yeah. So, hi everybody that's here in person. This is a triple threat attempt to do this defense. Everybody here live, plus our participants on Zoom, plus whoever's watching on YouTube. So we're YouTube live streaming this, so it will live as well. And this is Rocio's thesis defense. After 5 years of work, she will be presenting the work that she's done. So not everybody here has heard everything. It's for the committee who is also here, Emily, Kelly, myself, Ruth, Ari, and Sarah, who's in Germany. And while I think defenses kind of run the muck, depending on what university you are at, in my opinion, this is a celebration in many ways of all of the work that Rocio has done for the past 5 years. And it's our way of, for those that haven't heard about the work, to listen to it, for the committee's chance to hear about it in even more detail with her unique voice. But in so many ways, this is a celebration of the accomplishments of our Argentinian firecracker. So I'm going to let Kelly, who is the co-advisor, Kelly and I have done this as two mothers, academic mothers, give the rest of the intro for Rocio.
All right. Thanks, everybody, for being here online and for coming in person. I'm super excited that we've been able to, and to Jackie and Rocio yesterday for doing all the work for making this hybrid event possible. But today it's about Rocio. And I just wanted to take a second to say how proud we are of all the work that you've done. In particular, how amazing you were at navigating all the advisors. And you are, especially for everybody out there, Rocio is an amazing collaborator. And she's great at taking in input from lots of people and making the work your own, even though there were lots of opinions getting thrown at you at the same time. I'm really proud of this work about M-dwarfs. I think it's a field which is going to continue to grow and where you're going to make a huge amount of impact on the ages of stars, both of M-dwarfs and potentially of all at other masses as well. So we're really looking forward to your future work as well. I think with that, let's get it done. The floor is yours.
Do you want to hold questions or?
Yeah. Okay. So.
My thoughts were that the committee can reserve questions until the closed session, which will happen after the public version. And I think maybe we should hold questions until the end, just because Zoom coming in. I mean, if there is something.
What do you prefer about questions during your talk, or do you prefer people wait till questions at the end?
I'm good if you want to ask during.
Okay.
I'll just repeat them so everyone on Zoom can hear because.
Mm-hmm. And I'll be monitoring Zoom. If folks want to put clarifying questions in the chat, I can also help field those. But then we will have a regular question period at the end for everybody, and then we'll ask folks to leave. And then the committee will have some time to ask questions, and then we'll ask Rocio to leave, and then we'll have some discussion, and then we plan to reconvene by the Nobel Prize statue in the park. Probably around 11:30, 12.
Nobel Prize statue?
The Nobel Prize statue at the base of the stairs to the terrace.
Okay.
Public property, not museum property.
All right, ready.
Okie dokie. All right. Is that good? Can everyone see it? Oh, good. Well, I guess we're enough that this is not necessary, but just in case. Thank you for the introductions. That was very moving. So welcome everyone to my defense. My thesis project is called A Unified Approach to M-dwarf Ages, and has been done with the two people that you just seen, my two advisors, Kelly Cruz and Jackie Faherty. So I hope you enjoyed the presentation as much as I enjoyed doing the work. Come on. So I'd like to start with the statement that stellar age is one of the key fundamental properties in astronomy. There are several fundamental properties, such as effective temperature, radius, metallicity, luminosity, and mass. But if we want any chance to study these properties and how they evolve, we need ages. That's why the statement. But that's not all. If we want to study galaxy evolution, we need stellar ages. If we know the ages of a star in a certain region of a galaxy and the ages of another region, we can attempt to understand how they got there. And in addition, we can also study planetary evolution. Currently, the only way to get ages for exoplanets is with the age of their host star. So if we want to study how that planet evolved, we need to get the ages of the star. And the list goes on, but I'm going to stop there. One of the unsolved problems in astronomy right now is M-dwarf ages. I'm going to use M-dwarfs and low mass stars interchangeably during this talk, but that's not always the case. Just warning you. And as this representation is showing, M-dwarfs are smaller than the sun and in comparison also to an exoplanet. So M-dwarfs are the coolest stars in the galaxy, and they are also the most common star in the galaxy. They are everywhere, so they can help us understand how the galaxies form. Everywhere you look at, you're going to find an M-dwarf. If you know their properties, you can use them to study the galaxy as well. But that's not all. They are the major targets in the search for Earth-like exoplanets. Therefore, if we want any chance to understand how these planets evolve, and maybe if they are even habitable, we need to understand the properties of the host star. And this is where studying M-dwarfs becomes so important. To give you some characteristic of M-dwarfs, this is the color magnitude diagram from my first paper. From Gaia DR2, where we have the absolute magnitude in G in the y-axis and the red color in the x-axis. And we can see the beginning of the red giant branch, the white dwarf, and at the end of the main sequence, the M dwarfs and Ls at the beginning of the L. So M dwarfs have around 0.1 to 0.6 solar masses, so even less than half of the mass of the sun. They have temperatures of 2200 Kelvin and between 2200 and 3800 Kelvins, and have a radius of 0.1 to 0.6 solar radius. They are so small that they burn their hydrogen in their core very slowly. Therefore, their main sequence age can be very long, even longer than the current age of the universe. So in Jackie's words, every M dwarf that has ever lived is still there. They have not evolved to the next stage. Therefore, if we want to study stellar properties, this is a great start because we have a wide range of ages. So let's compare M dwarfs to higher mass stars. Our sun is a G2, so we have G and Ks, which are higher mass stars, and then we get to early Ms, M0 to M3, and later M3s. So if we compare the luminosity, radius, and mass, we see that decreases as we go to later types. That makes M dwarfs harder to observe and therefore to measure properties and to study than higher mass stars. But also, their main sequence age is longer, as I was saying before, which makes their properties change very little with time, and makes all those properties harder to study as a function of time if they change very little. That's not all. Solar type stars or higher mass stars are partially convective, meaning they have a radiative core and a convective envelope. This is what we know, we understand from our sun that is close by. When we go to early Ms, they are still partially convective, but they have a thicker convective envelope. This envelope gets thicker and thicker as we go to later types, until for later types, they become fully convective. Therefore, M dwarfs are harder to study because they are fainter, they are smaller, they have longer main sequence ages, and their physics changes enough to make the models do not work and do not reproduce the data. So, they are very challenging. There are certain methods to measure ages of higher mass stars, such as isochron fitting, astroseismology, and gyrochronology, which you can ask me about them later. But given all these properties that I was telling you about from M dwarfs, all these models do not work. There are other methods for higher mass stars, such as empirical and statistical age relations. This is finding parameters which are related to age, understanding how they evolve with time, and then using those to get an age of a star. These are the key to study M dwarf ages. And I'm going to tell you about which parameters. So what parameters can we use that are related to age to get ages of M dwarfs? We can use parameters as the color magnitude diagram position, kinematics, magnetic activity, and rotation period. During this talk, I'm going to describe each one of these parameters, but I just want you to have a clear view of which ones are they. So in the history of low mass stars ages, these parameters are usually used separately, which can result in a very imprecise age, or combine approximately, like this work from Adam Burgasser in 2017, in which they combine different age indicators in an MTMC to get the age of TRAPPIST-1, which is an M8. But we want to use a more robust method. So the method I'm going to talk about was based on the work done by Ruth Angus in 2019, where they realized that by combining two age dating methods, they could obtain a better age estimation. So in this plot is the BP minus RP color in the x-axis from Gaia, and in the y-axis is the age. All of these stars are part of the same open cluster, the NGC 6819. And if we look at the orange triangles, we can see that the age estimation is better for higher mass stars than for later mass stars. This is the orange triangles are the result of estimating ages using only isochron fitting. So what we can see is that for lower masses, so the late G and Ks, the estimation is worse. That's because the isochron is starting to fail. But if now we concentrate on the black points, we can see the estimation becomes much better, though that is the result of combining isochron fitting with gyrochronology in a Bayesian framework. So what they realized is that the age estimation became much better when including the gyrochronology in this Bayesian framework, because the gyrochronology works much better for later types and improved the age estimation that the isochron was not getting well. So based on this idea, what we wanted to do, or we set up to do, is to define a method to get ages of M-dwarfs by combining different age indicators in one Bayesian framework. Those age indicators are going to be H alpha, kinematics, and color. I'm going to talk about them all, but in principle, just mentioning them. There were several steps going towards this goal, and are going to be different sections in this talk. For the section 1 is called Exploring the Age-Dependent Properties of M and L dwarfs using Gaia and SDSS, which is basically studying color magnitude diagram position and kinematics as age indicators for M dwarfs. The second section is the calibration of the H alpha age activity relation, so how H alpha evolves with age for M dwarfs, of course. And in section 3, I'm going to tell you about the method that I developed to estimate ages, this combination of all of these parameters in a Bayesian framework, which I call M-dwarf date. Last, I'm going to tell you about the conclusions of the work and the future work. Okay, so, and I forgot, in section 3, I'm also going to tell you how I'm planning to include rotation periods in all of these estimations. Yay, Mark. So section 1, again, how we use color magnitude diagram and kinematics and study them as age indicators. So let's talk a bit about color magnitude diagram position as an age indicator. The color magnitude diagram is a proxy for this plot of luminosity as a function of temperature. If based on stellar evolutionary models, we can trace lines in this plot that are of constant age. Like this simulation is showing stars of the same cluster, therefore they have the same age, and we can see them with time evolving into the main sequence, which is marked with this green line, and then out of the main sequence once they go into the next stage. But if we concentrate on the low temperature or low mass regime, we can see that the stars stay in the same position for a long, long, long time. This is because the luminosity of M-dwarf changes very little with time. Therefore, if we want to find the closest curve of same age to the star to get the age of the star, we're going to find that a lot of curves are in the same place. So we cannot use them as an age indicator. And also, the stellar evolutionary models are not very good to reproduce the position of M-dwarf in the luminosity temperature diagram. So what we set up to do, is to find a relation between the color magnitude diagram position and age based on data, so empirically, meaning try to see where an empirical isochron would go through. To do that, I need a big, giant sample. So I started from the combination of two samples, the West 2011 and Schmidt 2015, that had M and L dwarfs from the Sloan Digital Sky Survey. Therefore, they have low resolution spectra, all of them. This sample contains more than 74,000 stars. And as they have low resolution spectra, they had measured H alpha equivalent width, which, so for now, trust me, that is a magnetic activity indicator and therefore an H indicator. I'll tell you more about it later. Spectral type classification, and radial velocities. I cross-matched this sample with Gaia DR2 to obtain parallaxes and proper motion. And I found 91% of the sample in Gaia. Therefore, we have a big sample of M and L dwarfs with 3D kinematics and H alpha equivalent with both H indicators. So far, trust me, but I'll get to them. This was the work, my first author paper that was published in 2019, and it's also the chapter 2 of my dissertation. This is a sample, the color magnitude diagram, absolute magnitude in G in the y-axis and the red color in Gaia in the x-axis. And I'm going to point out that this is a very clean sample. I adjusted the quality cuts suggested by Gaia to make them suitable for the end of the main sequence and get the best photometry and astrometry possible for these stars. So on that note, we can still see a lot of scatter in this plot. This scatter can be caused by several different reasons. For example, binaries, which would make the stars look brighter, low metallicity, which makes the star live in a very particular place, dust, which makes the stars look redder, and also the one that we're interested in, age. So to study the relation of the scatter with age, what we did was to color code this CMD with different age indicators. The first one is H alpha. As I mentioned, H alpha is a magnetic activity indicator. In here, I'm dividing the stars in active and inactive. All the inactive stars are in gray, and the active stars are color-coded by fractional H alpha luminosity, which makes that the more active stars are in yellow, and the less active stars are in brownish. So what we can see right away here is that for earlier star types, the more active stars, and therefore younger, have a very particular place in the CMD. They look brighter and redder, or like in this direction. So there are different causes to this effect. The one that we think could be happening is that these stars have their radius inflated. That is because they are magnetically active and the magnetic field makes them puffed up, which would make them look redder at constant volumetric luminosity, make them move in the direction that these stars are going. What we can see from this plot is that young stars, the CMD is giving information also about the age of the stars. Those are the young ones, the ones I was talking about. So the other age indicator I want to describe is kinematics. So kinematics is related to age in the sense that stars are born close to the plane of the galaxy. So when they are young, they're going to have an orbit close to the yellow line in this plot. As they get older, they're going to interact with giant molecular clouds or the spiral lamps of the galaxy, and they're going to get separated from the plane, getting to an orbit closer to the green line in this plot. So let's put axes to this, and we would have the vertical velocity, so the VC, and the radial velocity, for example, in the galaxy plane. So using these velocities we can find different age indicators. So ways that measuring the 3D kinematics, we can get an age. These age indicators are the vertical or radial velocity dispersion, vertical action dispersion. The vertical action is a proxy for the highest point in an orbit of a star, and the tangential velocity. So let's understand how this works with the doodle. So if we plot the vertical velocity with respect to the plane of the galaxy as a function of age for different stars, we can see that for the young stars, the dispersion is smaller. So all have a small velocity. That's because they are all close to the plane. And as they get older, some of them are going to interact with stuff and going to get kinematically heated. Therefore, the velocity is going to get higher. So if we measure the dispersion in different beams of age, we can see that the dispersion increases with time. And this is the age-velocity relation that we normally use to get ages of stars from kinematics. So as I mentioned in the sample that I was describing before, I have 3D kinematics for all of the stars, or for a big part of the sample. So what I did was to study 3D kinematics in the CMD using tangential velocity. So what we can see right away is that there is a group of stars below the main sequence that live in the place where usually low metallicity stars live and have tangential velocities of around 250 kilometers per second, which agrees with the population of thick disk or halo stars. Therefore, low metallicity, thick disks or halo stars, meaning separated from the plane. This is a group of old stars. Therefore, right away we can see that there is a place in the color magnitude diagram which indicates that the stars are likely old, therefore having a relation between the two. So again, I have two H indicators in the sample, H alpha and 3D kinematics. They are both H indicators. They should be correlated. And that's what I looked in this plot. In this plot, there's a lot of things happening, so I'll go slowly. In the vertical axis, we have the dispersion in vertical action, which I calculated in bins of H alpha. There are two panels. In the left panel are inactive stars according to H alpha, and in the right panel, active stars according to H alpha. And for the active stars, for which the H alpha value actually says something, I calculated the vertical action dispersion in bins, as again, of H alpha. And this is calculated for the 3 different bins of spectral types. So what this plot is showing is that active stars have a low vertical action dispersion, meaning that that is a group of young stars. And then less active or inactive stars have higher vertical action dispersion, meaning that they are old. Therefore, 2 H indicators that are for M-dwarfs and that correlated, confirming that both are H indicators for M-dwarfs. Okay, takeaway points from this first section before I move on. So using Gaia DR2, I redefined the color magnitude diagram for M-dwarfs. So now we have a very precise color magnitude diagram where we can study in detail each feature. I found that there is a relation between color magnitude diagram position and age for M-dwarfs using H alpha and kinematics. And I found that the fractional H alpha luminosity and vertical action dispersion are correlated for M-dwarfs, confirming that they are both H indicators. Are there questions so far? Just gonna take one. Okay, so this was my first author paper again. So I'll move on to the second part. Section 2, calibration of the H alpha H activity relation. H alpha is a magnetic activity indicator, as I mentioned. So let's talk about magnetic activity for a bit. So this is what I think of when I think of magnetic activity usually. This is a video of the sun where they took different images with a short period, separated them. And what we can see here are these lines of magnetic field going out of the star and in back, making a loop, and also lines that go out of the star and into the infinity. These lines are generated in the dynamo of the star inside. That dynamo is between the radiative core and the convective envelope that I was just describing. Those lines are going to go out of the star through the atmosphere, hit the different layers of the atmosphere of the star, and generate different types of emissions that we can measure. Those emissions are H alpha equivalent with UV luminosity and X-ray luminosity, among others. There are more, but these are one of the ones that are mostly used. This magnetic activity is going to be strong when their stars are young, and it's going to decline with time, the magnetic field strength, and also these emissions. This is going to be correlated with rotation period, which I'm going to talk about later, but so far, this is going to, I'll just leave you with the fact that stars spin down, and as the stars spin down, the magnetic activity decreases with time. The indicator that I want to concentrate today is H alpha. H alpha is the first Balmer line and is marked in this spectrum of a very active M3 to the left with blue vertical dashed lines, all of the Balmer lines, and the H alpha is at 6.563 angstroms. This line is generated at the chromosphere of the star, so the first thin layer after the photosphere. And one thing that we can see here in this spectrum even is that the H alpha is usually very strong, which makes it very easy to measure, even from low resolution spectra as this one, which is from the Sloan Digital Sky Survey. So very easy to measure. We can get a lot of them, but we actually are going to need it because the downside of H-alpha is that it's extremely variable. So if we want to study H-alpha, we need lots of them. There are a lot of indications in the literature that H-alpha is correlated with age, but there is no empirical calibration of how the H-alpha evolves with time. And that's what I set up to do. And to study how the H-alpha evolves with time, what I did was to collect a sample from the literature that had H-alpha equivalent width measurements. Equivalent width, just as a reminder, is the area below the line or above if it is, this is because it's an emission line. So a lot of H-alpha from the literature, a big sample from those. And I looked for ways to get H's for that big sample from the literature. And I used two methods. One was to look which ones of these stars belong to young associations, known young associations, which are well characterized and have a well-known age. I found 871 M dwarfs from young associations using the code Banyan Sigma, done by Jonathan Gagne, and that identifies members from the closest associations using kinematics. So with this, we got a probability of the stars belonging to a certain group, and we use that probability to define which ones were actual members. And as I mentioned, all of the stars are from the same young associations. These associations are born at the same time, so all of the stars have the same age. And if we can get the M dwarf that say that the M dwarf belongs to that group, we can get the age of that M dwarf, even though we don't have other methods. Okay, so the second method is to look for binaries with M dwarf. If we can assume two stars are born, if they are in a binary, they were born together at the same time. So if we can get the age of one, we can assume the other one has the same age. So what I looked for was M dwarfs communing with a white dwarf. White dwarfs are particularly useful because they have very well-defined cooling sequence. So we can get for how long the star was cooling, and combining that with stellar evolutionary models to see how long the progenitor star lived, we can get the total age of the star and assign that age to the M dwarf. I found 21 comovers in the sample. These are white pairs, therefore we can assume they did not interact as they were evolving. So we can assume those are field stars and use them as calibrators. The age of the white dwarf, I calculated it with a code that I made called WDwarfDate, which estimates ages of white dwarf innovation framework from effective temperature and surface gravity of the white dwarf. And this is a paper that is going to be submitted sometime soon, I hope. And all of this work of the calibration of the H-alpha relation was my second first author paper, which was published in 2021, and is the third chapter of my dissertation. So let's look at the results. Here I'm showing you the H-alpha equivalent width as a function of age. In gray, all the dots that are gray is the whole sample. And I'm color coding with purple M0s to M2, so early M dwarfs that are partially convective. And in gray, there is at the bottom, we can see where is the limit where the stars are inactive, approximately. In a point are shown the stars that belong to a young association, and in a 5-point stars are the M dwarfs that are communing with a white dwarf. So that's why they are the oldest, and we can see them to the right. So right away, what comes up is that H-alpha decreases with age, H-alpha equivalent width. And we can, I did the same analysis for mid-Ms, which are fully convective, so M3 to M6, and ultra-cool dwarfs M7 to M9. They all show this decrease in magnetic activity, we don't have enough information to constrain how the decrease goes for ultra-cool dwarf a lot, but we can see it decreasing. So that's the main idea. For the interest of time, I'm not going to show the actual fit to this relation, but if you want to know more, ask me later. But I'm going to go to another way of calibrating the magnetic H activity relation using H alpha, that is the active fraction. So I'm counting how many stars are active in a bin of color. If we concentrate first on the black line in this plot, which is showing the G minus RP color in the x-axis and the active fraction in the y-axis, we can see that once we go to later types, the active fraction increases. This was calculated from a sample of field stars, therefore just grabbing a sample of stars that from the galaxy. So what this means is that later types, when we grab a sample of later types, we will find more stars that are active than if we grab a group of earlier stars. This can be explained if earlier stars stay active less or later types stay active longer than earlier types. That's why we can see the active fraction increasing. What I did was to find that this active fraction also decreases with age. So we can see the different age color-coded with different colors, and we can see how it's decreasing into this field population of stars. But we can also see that this decrease is not happening in the same way for earlier types and later types. So active fraction is decreasing with time, and that decreases depending on color or mass. There is another way to look at this and to calibrate this relation, which is switching the axis. So if I plot the active fraction as a function of age for different spectral type bins, we can see this very particular decrease of the active fraction. So if we call the active fraction this AH alpha, which is 1 for active stars and 0 for inactive stars, we can see that the dependence of the active fraction is as an exponential, a decreasing exponential that goes as dH divided at T0, which is a characteristic active lifetime of a star. We can measure this T0 by feeding the data. So in the label, you can see the different T0s for the different spectral types. What is showing is that this T0 is increasing for later types, which agrees with the previous statement that I made before, that later types stay active longer. If your attention is being called to the M4s, which have a 31 gigayear old, that we check that is not correct. That is the result of feeding the data. And if you can see the red points, there are no points older than 1 gigayear. So once we get more points, that T0 is going to be lower. If you want to ask me later about that analysis, please do. All right, but so this is great. This is a great relation of active fraction as a function of age. But once H alpha becomes inactive, that's it. It's not indicating anything else about age. So if we want to be able to estimate older ages of M dwarf, we need to combine that H alpha with different age indicators, as I mentioned at the beginning of the talk. But before going into that, takeaway points. So I found the first empirical relation between H alpha and age for M dwarfs. I also found that H alpha actually decreases with age. And I found that there is a relation between active fraction and age, and it decreases with time, and it depends on the mass or the color of the star. Okay, questions? While I breathe. Next, third section, and this section is the method to combine different age indicators for M dwarf innovation framework to estimate an age, which I'm going to combine H alpha, kinematics, and color that now I have described them all. And this method is called M-dwarf date. So just to make it super clear, these are the 4 indicators I'm going to talk about in this talk. I'm going to combine these 3 in the method to estimate ages right now, at least. So let's put it in another direction: magnetic activity, kinematic, color magnitude diagram. For magnetic activity, I'm going to use the active fraction versus age, so that exponential that I showed you before. For kinematics, I'm going to use the h-velocity relations for 2 velocities, the vertical velocity and the radial velocity in the galaxy. The h-velocity relation, as a reminder, is how the the dispersion of the velocity evolves with time. And for color magnitude diagram, I'm going to use the G minus RP color, and I'm going to repeat the procedure, changing the parameters which depend on color to estimate ages. That's how the color is going to go into this model. So all of this is going to go into one likelihood that is going to depend on the parameters of the models alpha. I'm going to run that in an MCMC to obtain an H probability distribution function as a posterior. So that's the basics of the method. So let's look at the H probability distribution in more detail. So this is the posterior, which is the age, the probability of the age given the parameters that I just described: vertical velocity, radial velocity, active fraction. This is going to be a 1 or a 0, and the parameters of the model. And it can be written as a likelihood, which is going to be the multiplication for the likelihood for each one of the parameters: the vertical action first, the vertical velocity, the radial velocity, and the active fraction as the last part. It's going to be the combination of all those. And the priors, which for the age is going to restrict the age to be between 0 and 15 gigayears old, to not cut it on the age of the universe and allow it to go a little further. And the priors on the parameters of the model are going to indicate that those parameters are going to be fixed. That's going to be the prior on those parameters. So looking at the likelihood a bit more, for the kinematics part of this relation, this is what the likelihood looks like. It's going to be an exponential centered at 0 with width of that Gaussian that is going to depend on the error of each velocity and a factor that depends on h. And that factor is at sigma t bc or br. And that factor is going to be given by the h-velocity relation. And the AC, BC, AR, BR, that maybe you can see my mouse. Those 4, are going to be fixed. Those are the h-velocity relation, so how this dispersion evolves with time, and that's going to dictate how this Gaussian looks like. And last is the likelihood for the active fraction, which is going to be that exponential that I showed you before, which basically is saying the probability of a star to be active as a function of age. And that T0 is this one over here. It's going to depend on color. So this is why I'm running for different colors, changing that T0 each time. And that's where the dependence of color goes in. And that probability of H alpha is going to be the exponential if the star is active, and 1 minus exponential if the star is inactive. And I'm going to run all this into the amazing PyMC3, which runs super fast and is great. Okay, so again, the likelihood is going to be, the model is combining the h-velocity relations and the active fraction that I described before. And I'm going to run this model each for the different colors. So that was the model. That's how it works, the method. To test it, I ran it in different samples. One was with simulated data, so simulating ages, from those ages calculating parameters, and from those parameters trying to retrieve the ages that I simulated using the method, this M-dwarf date. I also tested it on the calibration sample from my second paper, which I just described, the young associations and M dwarfs coming with the white dwarf. And last, I ran it on the first sample that I described, which is this big sample of M dwarfs with 3D kinematics and H alpha, plus the Newton et al. 2019, which also has H alpha, also has 3D kinematics, and has some rotation periods, which makes this big sample to have at least some rotation period. So we have H alpha measurements, 3D kinematics, and rotation period. For the sake of time, I'm just going to describe two of this, the simulated data and the last one, the one that doesn't have ages, and I'm just going to calculate them, but you feel free to ask me about the calibration sample after if you want. So for the test on simulated data, in this plot I'm showing you an example of an age calculated using M-dwarf date with the PDF in the y-axis and the age estimated in the x-axis, and we can see the whole distribution. The true age is marked with a vertical dashed black line, and I'm showing you two distributions. One is using only 3D velocities to estimate the age, and the other one is combining it with H alpha. So what we can see is that the age becomes much better when including H alpha, which is what is expected, that by adding other age indicators, the method works better at constraining the age. However, we do see that both point towards the right direction although they are not super well constrained. This big tail that we can see in the distribution is caused by the fact that with the age velocity relation, we cannot discard older ages if the star has a small velocity. It could, like I showed you, if you remember that plot, that the velocities dispersions were increasing, some of the stars still had small velocities. So it's less likely, if the star has a small velocity, it's less likely for it to be old, but still not impossible. So that's why that long tail happens, and it's going to be present everywhere. So let's look at an example of a slightly older star of 6.78 giga years. Again, with the two distributions, we can still see this effect of the age estimation becoming better when including H alpha, but still the precision becomes worse when going to older ages. However, we do see that is pointing into the right direction. And for an even older star, the two distributions are basically the same. That's because now the H alpha is inactive. So basically the method is just using the 3D kinematics. So it's not giving a lot of new information. The precision is not great, but still it's going into the right direction. That's what we care about because we can improve the precision. Okay, so now I'm going to describe how I applied this M-dwarf date to a sample of M-dwarf which doesn't have ages, but has all what I need to estimate that age. That is the combination of the first sample that I described and the Newton 2019, which has H alpha measurements from the Sloan Digital Sky Survey and from the MERTH project. It has 3D kinematics from Gaia, and it has rotation periods from the MERTH project. So I have these two to estimate the ages. That's what I need so far for M-dwarf date. And I'm going to tell you about what I found when plotting the rotation periods that I have as a function of the ages that I estimated and what conclusions I can get from that. But first, let's talk a little bit about rotation period as a function of age. So rotation period indicates how fast the star is spinning, and we can measure that from looking at the star spots in the star generated from magnetic activity going in and out of view of the star. So it's going to generate a change in the brightness of the star. This rotation is going to go, so the rotation period is going to become longer. So the star is going to spin down with age. This is caused by the magnetic field and a process called magnetic braking, which makes some particles of mass of the star being separated from the star with using those magnetic lines and going out of the star, which makes the star lose angular momentum and therefore spin down. But I mentioned before that magnetic activity is generated from rotation period. That is because the core, the radiative core, and the convective envelope rotate at different speeds, and in the middle, you can find the dynamo being generated. So the rotation period is going to cause this magnetic activity, and the magnetic activity is also going to help to make the star spin down. So rotation period and magnetic activity are tightly correlated, and they're going to go down with time together. Spin down, and the magnetic activity is going to decrease. So this is the sample. So the rotation periods from the sample that I just described, and the estimated ages in the x-axis. We can see there is a bunch of stars that are fast rotators at the bottom, so smaller rotation periods, it means faster rotation, and then a clump of stars at the top, which are slow rotating. These are mostly M3s and M4s. There is one M2 or two M2s, but mostly M3s and M4s. So fully convective stars. And I'm going to add more things to this plot, so it's going to get messy. I'm going to add Proxima Centauri, which is an M5.5. It has a very well-defined rotation period and a very well-calculated age because of two stars in the same system, which are solar-type stars. So we can get that age very, very well. And also Proxima Centauri is our closest star, so we can measure it very well, or as well as we can do for an M5. To compare these stars, which are oldish to younger stars, I'm going to add the stars that our own Mark Popichuk compiled from M-dwarfs from different young associations. And these are all the gray stars. Yes, thank you. So all of these M-dwarfs belong to a young association, so we know their age very well, and they have rotation period measurements. These two lines are the gyrochronology relation for higher mass stars. This was obtained by Ruth Angus in 2015. This relation depends on the color of the star. So it's going to give the relation between rotation period, color, and age. So I can just put in a color of an M-dwarf and see what that line looks like in comparison to the data that I have. So far it looks like if I want to fit this relation by eye, I would put it a bit higher, but that is something that we know that M-dwarfs spin down faster than higher mass stars, so that's something that is expected. The cool thing, or the nice thing about this gyrochronology relation is that when stars get to this point in their life, they evolve. The rotation period evolves with time independently of the initial rotation period. So we can estimate the age of the star from the rotation period because they all behave in similar ways. This happens for higher mass stars very early on. They converge into this sequence when they are very young, like around between 100 and 500 million years. So almost every high mass star that we find in the galaxy is going to be in that sequence. So we are going to be able to use the gyrochronology relation to get ages. That's not the case for M-dwarfs. And I'm going to add a few models just to be able to describe this a bit better. Where we have the slow rotator sequence is in blue. That means that the star started with a slower rotation period. It's going to be constant for a bit due to dislocking, and then it's that period where it's spinning up is due to the contraction of the star getting into the main sequence, and after getting into the main sequence, it's going to spin down and get into this gyrochronology relation, or this well-behaved sequence. This is a sketch of a relation. It's not an evolutionary model. It's based on other works, but it's just a sketch to explain this idea. And then we have the other type of evolution, which is fast rotator. The fast rotator starts with a faster rotation period and has a similar evolution as the slow rotator, But when it gets to older ages, it's still a fast rotator, and it's going to converge into the to the slow rotator sequence eventually. This is what happens for higher mass stars. The fast rotator converges into that slow rotator sequence very early on. As you can see in this plot, M dwarfs do not. There is a big chunk of old age stars which are still fast rotators. So these fast rotators, their evolution depends on the initial rotation period. So we cannot attempt to use a rotation to get an age because its evolution just depends on initial conditions. But we can use the ones that are here at the top because those are well behaved, or that seems to be in the slow rotator well behaved sequence. So if we want to attempt to include the rotation period into M-dwarf date, the method that I developed to get M-dwarf ages, we need to be able to distinguish between these fast and slow rotators. And we have one possibility, that is H-alpha. So here I'm color coding the stars inactive and inactive according to the H-alpha value. So what we can see is that all the fast rotators are active in H-alpha, and all the slow rotators, or what it seems to be the slow rotator sequence for M-dwarfs, are inactive. So this could be a very good candidate to distinguish between the slow and fast rotators and try to include rotation periods to estimate ages, because we will be able to include only the slow rotators. All right, so takeaway points from this part. I developed a method to estimate M-dwarf ages, which combined in a Bayesian framework. And those age indicators are magnetic activity, kinematics, and color. And I call that method M-dwarf date. M-dwarf date is working. That's in principle the goal. It's working. It is estimating ages and is going in the right direction. The precision is not the best, but we have ways to improve that age estimation, that is by including other age indicators. And rotation seems to be the next one and the one that we could get more information from. And it's a very good candidate. And we can include rotation period by distinguishing between the fast and slow rotators using H-alpha, which is something I'm going to be working on after. Any questions? But I'm almost done. So, summary. I developed a method to estimate M-dwarf ages, which I call M-dwarf date, and it's working. I found a relation between color magnitude diagram position and age using H-alpha and kinematic measurements. That was my first paper. And I found an empirical relation between the H-alpha and age and confirmed that magnetic activity, as indicated by H-alpha, decreases with age for M-dwarfs. I also found that the active fraction decreases with age, and that decrease depends on mass or the color of the star. And to include rotation period in this age estimation, we need to be able to distinguish between the fast and slow rotator. And H-alpha seems to be doing a good job at distinguishing them, and that's what I'm going to be working on. So future work, in September I'll be starting a position at the KITP, the Kavli Institute for Theoretical Physics at the UC Santa Barbara for a year, and then I'm going to be doing 3 years in Caltech, where I'm going to be working on different things, but among them is improving the age estimation of ages. And what I plan to do is, as I mentioned, include rotation periods, and also study ways of including metallicity, which is an age indicator that I did not mention, but also a very useful age indicator, an important one. I want to deepen the knowledge of M-dwarf evolution by studying the evolution of magnetic field topology and its relation to age and rotation period. And I also want to use all these ages that I'm going to be calculating to study the boundary between partially and fully convective interiors for M-dwarfs. So that's it. I'm done. Thank you.
Shall we take questions? Go ahead.
Yes.
Fantastic talk.
Thanks.
I guess my question is about, like, it's in section 3, when you talk about the rotations of gases. I guess my question is why, when they're the same age, and you will have these two different.
Yeah. So Lucy asked why there would be at the same age two such different sequences. So yeah, that's a great question. The main answer is that they started with a different initial rotation period. Why the M-dwarfs stay such long times with a fast rotation? It doesn't have a direct explanation. It could be related to the type of magnetic fields that they have. So these are fully convective M-dwarfs. The magnetic field is not generated in the same way as to partially convective. So the partially convective have the dynamo in the division between the radiative core and the convective envelope. For fully convectives, we don't have that boundary, but we still have a very tight relation between magnetic activity and rotation. We still see the same things as for the higher mass stars. So one explanation could be that the topology of that magnetic field is generating the star to stay active longer. But that's just one hypothesis. That's one that I'm probably gonna study later.
We have a question from Zoom
Okay.
that we can throw out, and you should repeat it because I don't think they can hear me from here. But Adam Bergasser was one of your academic grandfathers, so you could refer to him as that. He loves that. Grandfather, make sure you say that. He says, it looks like your method works best for mid-M dwarfs. Based on your research, what do we need to measure for ultra-cool dwarfs to get their ages with some precision? And how do we go into the substellar regime?
All right. So my academic grandfather, Adam Bergasser, grandpapa, is asking how, so that it seems that it's working better for mediums and how we can extend it to the method to get H's, how we can extend it to ultra cool dwarfs and the substellar. So for ultra cool dwarfs, the reason why it's working better for early mid-Ms, so it's not working better for mid-Ms, it's working better for early M, so everything earlier than M3. That is because the T0 of the H alpha relation of the active fraction, I was able to fit it only up to M3. So I did not include H alpha information for later types. So if we want to improve the H estimation for ultra cool dwarf, what I need is H alpha measurements for M dwarfs that are coming with something I can get the H for. So that's basically it, and something I'm going to concentrate later during my work as well. For the substellar, I wouldn't dare to say, because I would like to see how the H alpha works for the substellar. I would not dare to say that it works in the same way as for M dwarfs, but it would be interesting to study. I would say that the kinematics would work as well for the substellar object. So in that part, we could estimate an age with not a great precision, but with some precision or pointing in the right direction. I hope that answered the question. And Kelly, you had a question?
No, I was gonna.
Oh, the same.
Other questions from folks?
Yeah.
So at the beginning, it's like one of the motivations for studying M-dwarfs was to look for Earth-like planets. I'm wondering why M-dwarfs over other.
Perfect. So the question was that at the beginning I said that M-dwarfs are the major targets in the search for Earth-like exoplanets, and why those stars and no others. So I was too specific. It's in general the low mass stars, not only M-dwarfs. The low mass stars are fainter than higher mass star, and the Earth-like exoplanets are smaller. So the contrast when the exoplanet goes in front of the star is higher for a fainter star than for a very bright star. So it's easier to find them. But also, so just a matter of statistics, M dwarfs are a lot. They are everywhere. So they are the more likely star that we will find with an exoplanet. So those are the main two reasons.
Any other questions?
Can someone copy all the comments from the Zoom so I can read them later?
Yeah. We won't close the Zoom room
Okay.
right away either. So, in section 2, when you're talking about the H alpha, it seems like there's also like increasing dispersion of H alpha.
Yeah.
I guess I'm just wondering what that is.
So decreasing dispersion, kind of. So yeah, sorry. The question was that it seems to be a decrease in dispersion in H alpha with age, and why that could be. So there's several things going on in here. One is the variability of H alpha, which is basically the responsible for the scatter, or some of the scatter. And that variability, we think it is decreasing with age, but not in this regime of ages. So I did a study for the variability, and it wasn't like super decreasing. What it is happening here is that there is a very big difference with the scatter. Maybe that's what makes it harder to see between early M dwarfs and mid-Ms. Like mid-Ms seem to be super scatter in comparison to early Ms. So that is an intrinsic property of H alpha. The H alpha emission line is actually a combination between the photospheric absorption of H alpha and the emission from the chromosphere. So what is changing between early Ms and mid-Ms is that photospheric absorption. The value of the H alpha equivalent width is not like mid-Ms are more active than early M dwarfs. It's just that that factor of the photospheric absorption is changing from one spectral type to the other, and that's why it's important to divide the two of them.
Okay. I think that probably is the end to our open session. Should we try and do one more picture maybe with those on Zoom that are left here? Did you stop sharing this here? I've been trying to catch strange. Oh, okay, it's fine. I thought I just messed something up there. One more picture with everybody that's here on Zoom. If you guys that are there and are willing to turn your cameras on.
Yeah, Jackie turns her camera on, people can also
Yeah.
come around this camera.
And that's my dad over there.
Oh, you're real. You're actual.
Your actual dad.
If you guys switch in over here, I'm gonna try and take a picture of a picture. Well, man, I have an idea. We got a lot of cooks now in my picture-taking kitchen. Well, all right. I know. Let me try it a couple different ways, people. You guys don't worry, you're still in it. Can you guys rotate with me? Sorry, everybody on Zoom. Oh, this is cool. I like that. Can you guys? Battery's at 2%. So, Rocio, can you? She's fine. You're fine.
Yeah.
And you got okay. I got you guys there, and then I'll do another one from this side.
Yeah,
Okay.
it's such a hybrid.
Ready? The battery's at 2%. Okay, that's good. That's cool. I think that's a cool picture. Yay. Okay,
So we'll reconvene in a bit. Outside. Is that safest?
yeah, for those of you guys that are on Zoom, I guess, thank you for attending.
Yeah.
Thanks for coming. And if you want to say any kind words or maybe even clap, turn your
They were-
mics off.
Yeah.
Oh, you did that already? I
No,
don't
they
know.
were just.
You got the Chansky's entire family is
Yeah.
there.
Oh, no, wait, I got the.
All the girls. And
And
then
that's my dad.
and then that's your real dad. Hi. These hybrid things are so funny. And I'm not gonna. I won't close the Zoom room necessarily because Sarah, we need you. But everybody else can sign off. Say your beautiful words to Rocio.
Thank you for coming.
And now I end the live stream, right? Micah, I'm gonna.
Cerro.
Hola.
Ah. Buenísimo. Excelente trabajo, Ro.
Gracias.
Hablamos después.
Dale.
Chao.
Los llamo.
Who was recording? Was it?